Hello everyone, and welcome to day 3 of the notes, where what we're going to do is kind of talk about the construction of, some of our differential equations, so some mathematical models, and then just, show how we can use these applications to help us not only model the situation at hand, but then also to help us find, our solutions to our differential equations in terms of, what is the rate of change actually, what's actually happening here for the rate of change. So forgive me for how I'm going to have to do this today, just because I don't have any way to film as I write down. So I'm just going to go over kind of what I've already went over for the notes. So for step 1, when we're writing out the differential equation, we're looking at the model, and what we're doing is we're just going to remember everything that we've learned kind of in algebra to help us to distribute, or to help us translate the actual what's going on in terms of like an actual model or an equation. So to construct our models, the first thing is we want to identify the variables that are responsible for changing the system, specifically the level of revolution, and to setting a set of assumptions about the system. So let's go ahead and look at the first one for population dynamics. So assume that the rate at which the population of a country grows at a certain time is proportional to the total population of the country at that time. So just the model, that's real simple. It's going to be the change of population with respect to time. So that's the dp over dt. Let's see if I can grab my pencil, is equal to kp. Now again, hopefully y'all remember, directly proportional. That goes all the way back to an Algebra 1 concept of direct variation, y equals kx. Well, this way we know that, okay, if we want to assume the rate at which the population of a country grows at a certain time, that's the dp over dt, is proportional to the total population of the country at that time. So p represents the total population, and then k, that is going to be our, our constant. That's going to help us be responsible for our population change. So that's why it's directly proportional. So let's go ahead and use this model. Again, this model is not that great in actually determining the actual population, but it's one that has been used before in the past and actually correctly predicted the population change of America from the late 1700s to the middle of the 1800s. So example 1, imagine a model of a changing population of a community in which the growth rate is the difference between the rate of births and the rate of deaths in the community. Determine a model for the population P of T if both the birth rate and the death rate are proportional to the population present at time T is greater than 0. So what we want to do is we want to, birth rates, because that's directly proportional, that's just going to B is equal to K sub 1 times P. And because death rates are also directly proportional with, the current population, that's going to be D is equal to K sub 2 P. So we have two different, constants of proportionality, but they are both with respect to the population at a given time. So then our the rate of change of our population with respect to time is just going to be B minus D, because it's the difference of births and deaths. Well, we can go ahead and substitute in what we have for those, K sub 1P and K sub 2P, and then we can just go ahead and factor out the constants of proportionality. And so we have, our differential equation, our population change with respect to time, as K sub 1 minus K sub 2 times the total population. All right, for radioactive decay, assume that the rate at which the nuclei of a substance decay is proportional to the amount A of T of the substance remaining at time T. So here we have the model, and again, it's a direct proportion. It's directly proportional, so that, well, we'll move that so you can see. So that's just going to be D of A, because A is the total amount present, over dt is equal to Ka. So again, that doesn't change, except for, instead of saying P for total population, here we're saying A for total amount.